Welcome. My name is James Wormold, editor of Electro. In today's online panel discussion, we'll be exploring the world of infrared imaging and the capabilities it enables across multiple sectors, such as agriculture, life sciences, industrial inspection, and of course, defense. Infrared imaging allows systems and their users to see beyond what's simply visible and reveal information that conventional imaging systems miss entirely, whether that's identifying subtle material differences, detecting minor or major defects, analyzing biological processes, or enhancing situational awareness. Infrared technologies are helping engineers, researchers, and developers solve challenges that visible light imaging can't address. But building an effective infrared imaging system isn't just about selecting the right sensor. Success often depends on a series of design decisions made long before a system ever reaches deployment. Understanding which wavelengths matter most, how to maximize signal quality, and how to balance performance, complexity, and cost can all have a significant impact on the final result. And one component that sits at the center of those decisions is the optical filter. Often treated as an afterthought, optical filters can play a critical role in defining system performance. They can improve signal separation, enhance image quality, reduce unwanted noise, and reduce overall system complexity. So downplay them at your peril. We'll also be examining the role of the custom optical filter. While custom solutions can be perceived as being expensive, slow to develop, or reserved for only highly specialized applications, infrared imaging is one area where they can deliver significant benefits, such as reduction in development time or lowering system costs. Throughout the discussion today, our speakers will explore where infrared wavelengths offer the greatest advantages, the key decisions that need to be made when designing an infrared imaging system, the filter specifications that matter most, and the opportunities that technologies such as shortwave infrared are creating across multiple applications. We'll also hear some real-world perspectives, including examples of what success looks like when infrared systems are implemented effectively. So to help us separate the fact from the fiction when it comes to infrared imaging and custom optical filters, we've invited three industry experts to share their experience with us. So please welcome Brian Manning, Senior Application Specialist at Chroma Technology, Martin Ettenberg, founder of IR Consult, and Francois Corsaget, General Manager of New Imaging Technologies. Welcome, gentlemen.
Good morning.
Good morning.
So before we dive into the questions, however, a little bit of housekeeping. Today's session is being recorded and will be available to watch on demand for the next 12 months via the Electro website, alongside a full library of previous discussions. Back today, I'll be putting questions to our panel throughout, but we'd also like to hear from you as well, the audience. So if you've got a question, don't keep it to yourself. Send it in using Zoom's Q&A pop out at the bottom, and I'll put it to our panelists. And even if you're watching on demand, you can still submit questions and we'll make sure they're passed on to the panel. But without further delay, let's get started. So the first question I've got, Brian, let's kick things off with you in your corner.
Absolutely.
As an optical problem solver, what are the most prominent imaging challenges that infrared technology can be used to address?
Well, the first response that came to mind is one that's endemic in any type of imaging system, and that's noise. And the definition of noise can depend based on your application, depending on your imaging paradigm, what you're trying to look at. But it boils down to removing the stuff in your images that you don't want to see, but also, sort of emphasizing the things you do want to see. As far as the infrared itself goes, it eliminates a number of environmental conditions, whether those are room conditions, if you're doing something like QC in a drug company, or outside environments, fog if you're doing crop management from low orbit and that sort of thing. It allows you to determine what's going on in your sample, either through penetration or reflection, or both in some instances, and allows you to get at the meat of the question you're trying to answer without having an awful lot of quote unquote environmental noise to have to deal with. And it also uses the ability of materials or intrinsic ability of materials to have different absorptions to be able to differentiate between materials in vitro, in vivo, in situ, without having to do any real manipulations to the sample itself. And those can be obviously largely non-destructive types of methodology. So you're not damaging your sample while you're imaging them.
Right, so it's a high noise environments, and so Martin, what about you? Any other challenges that you can think of that infrared imaging specifically kind of helps fix?
Uh, in my eyes, it's always been seeing things you can't see with your eyes, right? Like the infrared is being pulled in to do inspections that you just can't inspect with your own eyes. You can detect things and look at things that just aren't detectable. Like for instance, looking at water content in something, it's very hard to just image and decide, right? But that's easily done in shortwave infrared with various filtering technologies, right? And or chemical detection, like if you're looking for plume detection of chemicals in the air, like this is something you can't see. There are ways to do this various detection um, with various methodologies, chemical detection systems, and uh, but it's much easier if you could just see it, right? And in the infrared, if you filter things out and you look in the certain wavelength bands, you can actually tell detections and see where like a cloud plume is, or a chemical plume is, or where there are foreign objects in your line where you want to pull out to make sure there's no, uh, glass in your coke in your beer bottle, right? That's broken, right? These are things that you really want to detect that are very hard to see, and that's where infrared, I think, really has big advantages because we're used to just perceiving the world through our eyes, right? And this gives us more than our eyes can see.
Thanks, Martin. And so, Francois, any other kind of lowering kind of noisy environments and seeing the invisible items? Any other kind of superpowers that infrared imaging brings you, Francois?
Well, seeing the invisible is actually seeing what you can't see. So seeing what you don't know
Mm.
either. So typically, if you look at the visible waveband, you're limited to 400 to 700 nanometers. Looking at the infrared, you're going from the 700 to the 12 micron wavelengths. So there is a huge variety of information in all those wavelengths. So you also need to know what you're looking for and what information is contained in each wavelength. So whether it is a contrast differentiating aspect of what you're looking for. So knowing what you're looking for also helps because you can also choose in what kind of technology you're looking for and what waveband is of interest for your system. And that is the tricky part of infrared is that you have so many wavebands, and each thing you'll be looking for will have a different behavior in all those different infrared wavelengths.
Right. So, I mean, talking about those specific the wavebands, what to dig deeper, what exactly is it about wavelengths in the infrared range in general that gives the ability to solve those issues? What is it about them there?
Well, so some materials will be transparent in one given wavelength and be completely opaque in another wavelength. So if you don't know the transmission of your material, you don't know what you're looking for. So that's why there's this aspect. There's also the ratios. Two different materials will have different ratios of reflection in different wavelengths, typically the vegetation. So you could be able to distinguish by comparing ratios in different wavelengths.
I would add too that it also using the infrared wavelengths will allow you to do your imaging in zero light conditions. So you don't necessarily, if you're again go using the crop management example, you can do it at night. It does not require visible light to detect what you're trying to detect. It is intrinsic to the material itself. So you do not need illumination per se for given applications, of course. Some you do, obviously, if you're looking at reflection and that sort of thing. If you're doing a semiconductor QC and that sort of thing, yes, you do need an ambient light to illuminate your sample. But for some applications, the infrared wavelengths will allow you to image in dark and do so as well as if you were doing it in light. In fact, it should be exactly identical for those applications.
Right. And Martin, quickly before we move on to a an audience question we've had in, Martin, are there any other kind of insights you can give about that infrared range?
Oh, yes. Oh, yeah. What you because you can't see it, you don't know what you're looking at. It can get tricky, and you have to be not knowledgeable, or at least talk to somebody. Yes, we were just talking about, you don't need light sometimes, but sometimes you really do, and those wavelength bands won't work at night. And we were talking earlier about signal to noise ratios, and these are important, and also just even when you can image at night, it matters when you're in these thermal bands like midwave and long wave is traditionally what's done without light sources. But you do have to worry about if you're outside. Now you have to worry about the sun heating and cooling your objects and creating this signal to noise background problems, and understanding what you're looking at and the imagery and how it's being produced is very important and will affect how you filter that light and understanding the filtering. So it can get complicated quickly, and but you don't know. It can, I'm going to say, hurt you in this imaging system because you're just unaware of what's out there.
Yeah, and we've got a couple of questions now come in from the audience. So if I go to the first one, which is basically on applications. So what applications do you see for sensors that are sensitive at lower wavelengths than typical SWIR in gas sensors, um, for example? Let's go to
Meaning,
yeah.
sorry, when you mean low, meaning, I'm sorry, so low meaning sensitivity, meaning low sensitivity to light, or we low wavelength. Like if we're looking at lower wavelength, obviously we have the visible, right? And Francois talked about up to 750, and then you start to move into the near infrared and shortwave infrared, right? And those are reflective, mostly reflective bands, right? And so you need a light source to either reflect off your object or transmit through your object to be able to pick up the signal and noise. And the biggest one in the lower band is probably water, is what's usually differentiation. It's somewhere around 1400 nanometers. But as you go higher up, you start to move into some gases and minerals, CO, CH absorption lines, and as you move up in wavelength, the molecules you can detect get more complicated, and so it's a matter of what you're looking for will influence what band and where you want to filter and pick up uh, your signal, the best signal to noise.
And what
Brian,
I would reiterate that the big one that immediately came to mind for again, depending on your definition of near IR and shortwave infrared, is water absorption at 1400. I think there's a secondary peak at 1800 nanometers. Um, Depending on what kind of imaging paradigm you're attempting, whether you're looking at water quality or you're looking at water absorption in a crop or something along those lines, um, you would depend on what you're actually trying to image as far as the wavelength of interest, but more importantly, what you need to negate, attenuate, block. I'm gonna harp on that point multiple times during this, but what you don't want to see is equally important, if not more so important than what you do want to see. So you want to, in that case, block visible light only to look at 1400 nanometers in a fairly narrow band, 1400 plus or minus a handful of nanometers, if that's what you're attempting to image. And there are examples up and down the electromagnetic spectrum of absorptions and or reflections that are necessary to detect while also eliminating other noise, again, to use that overly used phrase, of things that you don't want to see for that application. So there are, I mean, it's almost limitless. It all depends on the chemistry of what you're examining and its relation to the electromagnetic spectrum.
Hmm. I think how about specifically for quantum dot sensors, where I think they're
So,
included in the
for which
question.
sensors?
Quantum dot sensors.
Well, quantum dot sensors are not different than in-gas sensors. It's just a question of sensitivity. QE and also quantum dot sensors sometimes they have a very selective waveband, so it's more a solution to other SWIR solutions. So I won't necessarily go into the details of the sensor technology itself, but going back to the illustration of samples, for example, was mentioned the water absorption. There's also another main application, which is plastic sorting, for example. Plastics will not have the same wavelengths at the different reflection at different wavelengths. So the plastics will all appear the same color, plastic, transparent, and visible wavelengths, whether it's PMA, PET type plastics. You can distinguish them using shortwave infrared at different wavelengths by doing the contrast ratio of their different wavelengths. So that is another application where using selective wavelengths. Quantum dot is only a solution to get there that is in the long term probably less expensive than InGaAs, but with other trade-offs in terms of efficiency or in terms of complete wavelengths that you could cover with them. So.
Thanks. And so moving on to let's say practicalities. Let's say I'm designing an infrared imaging system, and I want to ensure sort of it has optimal performance, obviously. But what are the first questions I need to ask myself on that journey? What decisions do I need to make first before anything else? Francois, if you kick us off. Yeah.
Well, we mentioned it. The first thing is, of course, the wavelength. What is the wavelength of interest? What am I looking for? And then that goes to what kind of signal to noise ratio I'm looking for. I mean, what is my signal? What is my noise? And how do I get there to have enough signal to noise to be able to detect or see what I'm looking for? So those are the first, of course, the first two main criteria in my decision in the infrared system. And then there, of course, many others in terms of that can also, of course, with the optics, whether it's the filter or even the field of view I'm looking for in terms of resolution. So what are the details am I looking for in my object? What individual field of view I need on my system? Do I need a specific external lighting? Do I need my lighting to be itself multispectral, or should it be very selective lighting? So, but once again, that goes onto two criteria, which are which wavelengths and what SNR. So I'd say those are the two main criteria I'm looking for.
From a filter standpoint, I would concur immensely. Obviously, the first question is, yeah, again, which wavelength or wavelengths are you interested in imaging and studying? And again, to hammer home the point, what wavelengths are would you consider noise? From a filter standpoint, we would need to know whether you're looking to image a fairly broad range of wavelengths, or if you need nanometer or sub-nanometer resolution of a particular band. Obviously, the complexity of a filter that we produce is different in those two cases. A very broadband filter can be fairly simplistic. A very, very narrow transmitting band with a very wide out-of-band blocking ability can be very, very difficult to produce and therefore very expensive. The other thing that I would make a point of here is if you are trying to detect multiple discrete bands in a single image, that's a little bit getting leading the cart before the horse, and I'll get to an example of that towards the end of an application where that's being used currently. But it is something that people are doing out there and attempting to image simultaneous multiple discrete bands of various bandwidths. I would add to the things that people need to think about beforehand. We alluded to earlier, which was number one is the choice of detector and examining the quantum efficiency of the detector you're interested in. There's no sense in trying to image something if your detector is incapable of actually capturing that light or capturing it well. And from another filter standpoint, and Francois alluded to it, the thing that we need to concern ourselves with is the field of view. And as that directly pertains to the cone angle of light that would be approaching the filter that we're producing, we need to know whether or not you're imaging something at a microscopic level with a very, very narrow field of view and therefore a fairly limited cone angle, or if you're imaging hectare-wide crops, that's going to have, from low orbit, that's going to have a very large field of view, and the light hitting that filter might be coming at that detector and the filter that would sit in front of it at, nearly 180 degrees. We have ways of producing filters that are angle insensitive to an extent, but we need to know that up front. That's not a oh gee, I just thought of this midway through prototype. That's a base question. What kind of angle of incidence, well, I'm sorry, not angle, there's a good type of cone angle do you expect at your detector?
Okay, so before we move on to move further into the sort of optical filter range, so Martin, are there any other sort of bits of information you need to make sure you understand as an infrared imaging sort of system designer before you get
Yeah,
started?
I think the panels did a really nice job. Yeah, you have to look at this as a holistic thing. This isn't. It's not like you build this thing and you throw all the pieces together and hope it works. It is more of a holistic thing of what are you trying to detect, how fast are you trying to detect it, what's important in your detection. How big is the field of view? How big is the object you're looking at? What, as we would say, ground sample distance. How many pixels on the quote unquote target do you need to differentiate it? How many wavelengths of light do you need to? It's sometimes not just a single color. Well, I shouldn't say color, single wavelength of light that you need, right? And sometimes it's multiple wavelengths of light to actually differentiate object A from object B, especially depending on the environment you're in. In a factory, you can be more controlled in the light around you and controlling the signal noise and what you're looking at. When you're outside, you have to deal with the randomness of light that's out there, from cloud cover to reflection to the sun being out, the sun not being out, and everything else. And that's a different imaging problem. And so you have to deal with a different filtering solution to deal with that versus being inside in a controlled factory. So, and Francois alluded to it also, your detector in the end game matters as well as your light source, right? And then you have the whole optical train. So you have to look at this as the grand thing of what am I trying to do in the end game, and start building your system from there and differentiating these various parts. Otherwise, you'll get yourself in trouble, and you'll put some parts together that just are not going to help the situation.
Right. Thanks, Martin. So moving on to optical filters then. So how do I use filters to improve sort of performance? And what kind of things do I apply them for without overcomplicating the process, maybe?
Well,
Um,
the I was thinking about this in preparing for the panel here, and it dawned on me that we use the word filters all the time, and I don't think a lot of people really sort of stop to think about what the word filter may mean. You're not filtering anything in, and in my world, that's transmission would be filtering something in. Everyone says, I want to transmit this wavelength of interest, which is absolutely correct. You want to transmit the signal that you're interested in. I've told people, I have the perfect thing for you. I breathe it every day. It's called air. If you need something else, there's a piece of glass that transmits. What a filter does is to remove things. It's not designed to transmit practically. Well, it is designed to transmit, of course, but it's designed more importantly to minimize the impact of the other stuff that you don't want to see, the out of band, out of wavelength noise. So without the use of a filter to mitigate a lot of that extraneous noise, a lot of these systems won't necessarily work. That's the simple basic answer here, is that without the filters, none of this is possible. Yes, you do want an optic that or a filter that will transmit as maximally as possible your signal of interest, your wavelength, the range of wavelengths of interest. But it also needs, more importantly, and this is across all applications, whether it's SWIR imaging, biomedical imaging, any type of imaging, is the filter itself needs to block. And what it needs to block is the question that we at Chroma spend an inordinate amount of time dealing with, which is getting a sense for where people's noise originates. Whether it's illumination light, whether it's backscatter from some reflective surface, whether it's actual signal that from another molecule that might be close by, spectrally speaking, and that sort of thing. And the other thing that we, as a filter company, have to really demand upon ourselves is to maintain specifications and spectral precision across multiple optics. So we're, in a lot of these cases, yes, one filter going into orbit is fine, but it's a fleet of these systems going into operation at any given moment. And so every filter that we provide for that particular application, for that particular customer, for that particular imaging paradigm, they have to be nearly identical in spectral properties, in surface quality properties, in out-of-band blocking properties. I mean, they have to be, for all intents and purposes, exactly the same filter across multiple optics.
James, I and Brian, I am in agreement with you on I'm going to say most of that, but sometimes we don't want to scare everybody that this filter it has to be specified to the nth degree, right? Like there's a lot of times where you have an industrial application and you yes, in a space application where they're trying to image the Earth and doing military stuff, yeah, you want a Ferrari. But
Right.
sometimes a bicycle can get you to the place you want to go very easily, right? And you don't need a super deluxe filter. You can buy an off the shelf filter that just kind of takes care of the job. You may need to just block light below 1200 nanometers, and because that's where a lot of the light is sitting, and what you're trying to image is above 1200 nanometers, and it'll pick up your target very easily. As I said earlier, it's holistic, right? Like you need to look at the complete system, what your detector's doing, and what your imaging optics are doing, and what you're trying to detect. It may be the water absorption in the SWIR band with using an in-gas detector. The 1400 is pretty pronounced, right? And so you may be able to pick it up pretty easily if you're just kind of blocking everything below 1200 nanometers, and the reflection works, and you're in a factory and you have LED lights that are putting out 1400 nanometers. You're not picking up a lot of as we would say, noise from outside the band. And so you're kind of okay, and you can make it simple. Brian was just talking about when you're in a space-based application looking down the Earth, and yeah, the environment's all changing, and everything's changing around you, and you're dealing with the sun and various objects, and you the US government, the DoD needs that kind of precision, right, to do the job they need to do. But you may not need that if you're looking for, on your factory line, just to make sure there's not a metal scrap in when Cheerios are going down the line, right? And you just want to pick up that metal. It's a much easier filtering problem, and simple, especially with special lights, that you can take care of very easily. And so it's all in uh, the devil is in the details, right? And so you have to know what you're really looking for, and plain off the shelf filter may just get the job done, and don't worry about it. But as Brian said, if you're putting it on a satellite system going into orbit and it costs millions of dollars to launch, you better have the right filter planned out for all the angles, right? And that's what we're looking at.
Okay, and so Francois, so in your opinion, how do you make that decision, and how important are optical filters, and is that decision of what you want it to be used for really the most important thing to understand before you go ahead?
Well, as Martin said, for the camera, for the optics, and for the filter, it's also a holistic approach.
Mm.
Are you in the industry with the conveyor belts, and you have a push broom approach where you need to just go through different wavebands? Are you doing flash imaging where you need to have all the information at the same time with the coherence of time and not space? So do you apply the filter at the pixel level? Do you apply it at a part of the sensor level? Do you apply it outside the sensor with a filter wheel or with a Fabry-Perot cavity? That also depends on how many wavelengths you're looking for, what precision you need, what overlap you can accept or not, how fast the speed of the object you're looking at. So the solution of the right filter also depends on this complete system approach too.
So understanding what you want to block in your kind of application and where you want that to go basically is important. So is it then something that you need to start off kind of just decide on early before you start thinking about other parts of the system? Brian, maybe.
Yeah, certainly it should be an early concern. I mean, maybe not your very first, but it should be certainly something you're considering. Okay, how close do I need to get to the signal of interest um, in order to detect it sufficiently? I mean, nothing I don't believe is truly monochromatic unless you're dealing with Raman spectroscopy. You're dealing with a range. So of that range, what is of imminent importance? If you have signal, or I should say noise, to keep with the vernacular, that is spectrally close by, what do you need to do to eliminate that or minimize that its effect on what you're trying to image? Um, I don't want to, I have a couple of points that Martin brought up that are very important when you're just choosing a filter, and he alluded to it. You don't I don't try to sell somebody a Ferrari if they're trying to enter into Baja, nor do I try to sell somebody a Yugo if they're entering Le Mans. It really is dependent upon your application. The complexity of the filter is really dictated by its use. And as Martin said, sometimes an off-the-shelf optic will work perfectly well for you. A lot of times they do, and a lot of times you may need something that's a little bit more specific, a little more customized. Um, and the definition of custom here is a very, very fluid one as far as I'm concerned as a filter guy. Um, so
And and Martin, kind of so for any end users, let's change the question. For any end users watching who are on the hunt, let's say for the perfect filter, what kind of tips can you give them to make sure that they find it there?
Oh, it's funny. Whenever end users come to me, it's usually the question is, I have this imaging problem. Can I see it by X, right? And um, and if I've done it before, I can say, yeah, you can do it by X by doing, these things, right? But sometimes the answer is I don't know. I haven't done it, and so usually the next step is saying, all right, the object or the thing you're trying to detect, and we look at the wavelength bands that are necessary to go do that detection, right? And then at that point, you have to decide on what kind of filtering you'll need. And Francois alluded to it. Do you want to, how are you planning on imaging the system? Is it something just standing still? Is it moving? Are you moving? You have to look at this, as I said, this holistically as this whole imaging system, because then the filtering will matter, right? And are you going to use a multi-camera system? Are you just going to use a single linear array and scan it? And how are you going to combine these images? And so, um, before you decide on the filter, you have to really decide on, your kind of your imaging setup. And it's going to be a back and forth, right? Like, you may say, oh, I want to do this with one camera, and then you're going to go to the filter manufacturer, and the filter will go, wow, this is a really complicated filter. And you may say, oh, maybe it's just better, instead of making this complicated filter that I have to attach to my imaging array, maybe it's just easier if I buy these three simpler filters, and I buy three cameras, right? And I combine the imagery, and I do it by image processing, right? Like I can use the power of computers to kind of image processes. And I hate to say it, in the older days, image processing was very expensive, and so the filtering was a much cheaper and easier solution to go do this problem. And you built um, especially complicated filters, right? But cameras have now gotten much, much cheaper. Processing power has gone down tremendously, right? And so it may be easier now to just take three cameras and put three filters on that are a lot less custom, right? That are simpler to build. Put them in front of your cameras, and then do the image processing, and let the computer do the hard work, and this is a nicer way to do the system. And so there is a back and forth and trade-off thing, and you have to look at the various pieces. But as I said, it's holistic. You have to look at the whole system, what you're trying to image and what you're trying to achieve, because there are multiple ways to skin this cat, right? And so uh, you know, work with your camera manufacturer and your filter team, and do the trade-offs, and listen to what they have to say, because the image solution may be done by a better, simpler way, just by leveraging other parts of the system that are stronger, especially now with prices of cameras coming down so much, and imaging processing power going up so much faster than we used to have even 5 years ago, let alone 10. Brian, I don't know if you're seeing it, Peter, Francois, you're seeing the same thing.
Yeah, and Martin, yeah, on our side too, we've been receiving samples very often asking us, how can we detect, how can we see anything here? I'm like, I don't know. Sometimes in France we receive wine bottles, and they're asking us, how can we see through those wine bottles? So we tell them that first we have to taste it before we
Yeah,
try.
I was going to say, Francois, if you want help, with that, I'm willing to come out there to consult on helping with the wine bottle problem.
And, and I agree. Very often we have to try it out because we don't have the answer. We don't have the answer to all. I mean, everything is not available, and nobody just tried to test every different matter on Earth. So we don't necessarily know it. So we need to try it out and try which wavelengths work. So of course, there's always a lab test first to be able to analyze what is the correct wavelengths you're looking for. And then once again, I agree. For example, on convoy belts, now we're using line scan sensors. When you're using line scan sensors, you're better off using multiple sensors, each one of them having their own filter, because line scan sensors are much less expensive than an array type sensor. So once again, also depending on what you're looking at, maybe different, cheaper, smaller resolution sensors are easier to deal with if you're using multiple sensors instead of having one bigger resolution with a more resolved filter on top of it. But sometimes you don't have the space for it, so you need to have one single sensor with a high resolution filter on top of it. So once again, it is a complete picture that you need in order to be able to answer the problem. But once again, it always is a tricky problem because we don't have everything available. So sometimes it's very specific products that need to be developed.
And I would add too that you can often bounce those ideas, and not just us at Chroma, any of the filter providers, that bounce your ideas off of them. We love doing that. I particularly love doing that, hearing a problem and saying, okay, well, in the past I've helped somebody with something similar and we did this. Um, those type of interactions are hugely valuable. I feel like I'm learning something, and I believe that I'm helping the end user or the company or whomever I'm speaking with understand a little bit more about what we do and how that affects what they're trying to do. So being open with that information is huge.
Okay. So we're talking about being sort of selective with your decisions using sort of either multiple filters or sort of hybrid systems with image processing as well. So if I can bring it back again, because you touched on it, Brian, the use of custom filters maybe. What kind of risks do you run if you go off the shelf?
Well, and I'll back up for a second and make the point that custom, I always put custom in quotes because people come to me all the time for a custom filter. And yeah, we've done it. I did it 5 times last week. Just because it's custom to you doesn't mean it's custom to us. So the point that I want to make there is don't automatically presume that this is going to require something that we've never done before. More often than not, it's something we've done something very similar, and it's a matter of tweaking something or just, again, using a quote unquote off the shelf solution for that. Um, if you're not using filters that are custom and or specific to your application, yeah, I mean you're going to be dealing with the same issues you would be dealing with any imaging, low contrast, high noise, unwanted signals, things in your image you don't necessarily want to see, or things that you want to, minimize the impact of if it's a, presentation or a publication level type of application. You want to sort of be open with what you're doing, because even random information about your application can help us decide what might be required for your particular application. I'll drop back into visible land here for a minute, and I've had this conversation the last couple of weeks with someone doing machine vision, and the question is, Are you trying to determine whether the color green you're putting on your car is Bentley green, which I would imagine is a very, very select color or hue? Or are you just trying to determine whether you're painting it green versus red? In that case, the filter doesn't have to be very specific at all. It doesn't have to have high tolerances, and with that, the increased costs involved with that. I'll go back to end up my part of this with the thing I mentioned earlier, and we've alluded to a couple of times here, which is the filters that we make can be very angle sensitive. Meaning, if you're using a wide field of view or a high cone angle type of imaging, um, we kind of need to know that again from the outset, because we need to know whether or not this filter needs to be exactly the band it purports to be at 0 degrees incidence plus or minus 45, or 0 degrees plus or minus zero point 0.1 degree incidence, so on and so forth. So the more we know, the better equipped we are at finding a solution for someone, and the greater the possibility of not having to rely on what might be truly considered a custom solution, something we have never done before. Those types of solutions have never really, in my time at Chroma, really been a huge part of what I do, or what Chroma does in Toto. We typically have solutions for almost everything already. It's just a matter of figuring out what you're trying to do, and what we can do to meet that need in a way that isn't going to cost anyone time and money.
Yeah, so don't go in with any kind of pre-assumptions of how difficult it's going to be. Just because it's custom doesn't mean it's going to be difficult, I suppose.
Absolutely correct. Absolutely correct.
And is that something you sort of agree on, Martin, or do you kind of any other kind of risks you see with kind of going off the shelf there?
Um, well, it's always easier when you've seen it off the shelf and it's there and you can get all the specs and you can look at it and go, all right, it checks all the boxes and it's fine. The only thing I worry about with custom filtering, and I think Brian alluded to it, I'll more strongly emphasize, is you really should talk to your filter designer when you're talking to him. Yes, putting together a set of specs is a good way to start, but talking about what your application is and finding out where the specifications are loose and where they're really tight, and what's important to you is important to convey to them, because you may put something on the sheet and that may influence their design, or as Brian said, they may have done something very, very similar before, and they may have something that's not off the shelf, but it's damn near close, right? But you have to be, if you're talking to your team and giving them as much information as possible, you know, I know people always worried when sales guys are asking lots of questions, and you think they're being probing and nosy and so forth. There's a little bit of that, I'll admit. But the other part is they're really trying to help you. They have solutions behind them, and they're trying to figure out where your pain points are. And they may be able to get you a better, cheaper, easier solution that works well for you as well as for them, right? Like, having something that they've already built before and they're just making a small modification, or not even, it's just not publicized on the data sheet, makes life much easier versus you coming in and saying, I want X, right? And they're going to be like, all right, if you want X, then I'll force you with X. And that makes it more expensive. So the reason why we ask these questions and talk to you about the application is Brian said, we're trying to learn more, and we're trying to help solve the problem as simple as possible. That's how I see it. At least as a camera manufacturer and system manufacturer, that's what I was looking at. And when I worked with our filtering teams, that I would talk to the filtering guy and say, this is what we're trying to achieve, and they could get me a better, simpler filter than maybe I was originally seeing, because they've seen applications also.
Yeah.
Francois, you've probably seen that also, right?
Yeah. Custom optics, custom filters. Sometimes custom is just, for example, a push broom application. Sometimes it's just slicing the filter to the correct size of the sensor. So custom does not necessarily mean expensive, just dicing it to the correct dimension. And I agree, when we ask for questions, it's not necessarily to be able to just go into your system. It's sometimes to help you out, and sometimes you need that information in order to be able to help them through the best solution. And sometimes it is a custom filter that needs very precise and sharp rising and falling edges. But once again, if you don't have this global discussion on once again, I mentioned it again, but Martin mentioned many times the holistic approach. So you need that information, otherwise it's hard to answer. It's always has to be how do you say, a constructive mutual discussion approach.
Okay. And so if we take aside the cost aspect for a moment in terms of choosing a filter based on the specifications, I think you kind of used the story earlier on, Brian, about choosing a filter that can tell the difference between green or red or Bentley green and British race
Bentley
green.
blue, right? Exactly. Yeah.
How much does kind of performance come into it, and what kind of trade-offs are there between performance and or and how suitable it is to a certain application? How far can you push performance before in one area before it becomes too difficult to work with, let's say, in another area?
Well, and Francois just mentioned it. It's a combination of how steep do the slopes of the bandpass need to be, meaning how significant do we need to be to go from maximum blocking to maximum transmission. In the case of the red versus green, the slope of that bandpass can be fairly nominal. I mean, it doesn't have to be within a percentage of a nanometer from max blocking to max transmission. It can be slopey, in other words. It can look like a bell curve rather than a true square wave type of bandpass filter. Um, there are other applications where you absolutely need to be able to separate, 1064.0 and 1064.4 nanometers, in which case that means that the slope of that bandpass has to be very, very tight. Um, with that comes expense. The materials that we use to create that effect are expensive, and the more we have to use, the more expensive that optic gets. The other sort of factor in all of that is how wide do we have to think of the filter's blocking ability? Are we blocking out of band through the entire electromagnetic spectrum? That's being silly, but do we need to block visible? Do we need to block visible and out to 3 microns? With every additional sort of level of blocking, or do we need to block that range to an OD of 6 or an OD of 8, or can an OD of 2 suffice for what you're doing? That's something that the end user and it gets to dictate to an extent, and we don't know that off the top of our head. We can make suggestions about that, but that's again going back to my car color question is, and to determine whether a car is green or red, you really don't need a whole lot of out of band blocking to be able to do that. All of those things will filter into, pun intended, sorry, into the cost of the filter, the cost of the project. Speccing a filter to the nth degree generally, and not always, but generally means a more expensive filter than, well, here are my specifications, but my tolerances are plus or minus 100%. Okay, that's easy. We can do that. Filter companies have been doing that for 50 years at this point, even down to the absorption glass types of filters will do that kind of thing. So it really does sort of, what you're doing, how you're doing it, what's important, what we think is important, and a mutual understanding of all of that at the same time can affect all of this.
I can illustrate that with two really different sample applications. I had a customer. All they want to do is just detect the humidity in their any traces of humidity in their packaging. So that was pretty simple. Simple filtering above below 1.4.
Right.
Very simple. Then we had another customer. Their issue was quite tricky. They wanted to be able to distinguish all the different type of species of trees along the railway tracks, because to be able to know which routes could be damageable to the train tracks. And that, whether it's in the winter, in the summer, or in different periods of the year. And so you need to be able to have a very precise spectral response in those different weathers for all those different species. And then you need a very selective waveband to be able to really be able to distinguish with enough precision that information. So just two different examples where the needs are not the same.
And so what are the kind of were there any performance drawbacks when it comes to being that specific in projects, or is it really a case of if you have to go there, then you have to go there, or is it just cost?
It depends on also the time that is allowable for the application. I mean, are you running it once a year? Are you running it every day? It won't be the same cost. It won't be the same solution. So also it depends on how much what operating life you need for the system.
Right. And Martin, sorry, and Martin, from your side, then how does kind of performance relate to cost? Is that the only sort of balancing scales that you have to balance?
I think it's performance versus cost versus when you say performance, performance is lots of things. Like like how big an array do you need? How tight a wavelength band? Brian alluded to. Do you need blocking OD of 3 or 5 or 7? It gets back to that signal to noise discussion on what you need to actually differentiate what you're trying to differentiate. Are you trying to look at chemicals to parts per million or parts per billion, right? And that's a big difference, right? And sensitivity level that you need to get to. And so, yeah, I'm going to say performance is all in the eye of the beholder, right? And so it depends what performance you're going for. Somebody say, oh, I just need to image a small conveyor belt that's only 6 inches wide versus, somebody that goes, I need to monitor this entire factory to see if methane's being emitted anywhere at parts per billion, right? And you're like, parts per billion is a big difference from parts per million looking in a small area, right? So now your filter matters and your camera and how big a camera you're using. Do you need now a megapixel camera or a small 320 by 240 will take care of it, right? And this will affect the filtering system and your optical system and everything else on your performance. And so it depends what performance we're talking about, but these all matter. And yeah, Francois, it affects cost, right? It's a cost argument.
Well, while we're on performance, I can bring an audience question in, which is what about the fact that infrared imaging has lower resolution than visible wavelengths? What would you say to that, basically, Martin?
That was always a question that came up because you're dealing with somebody that you walk around with. I don't even know how many pixels are on my iPhone camera in my pocket now, right? I don't know if they're up to 20 megapixels or 50 megapixels or whatever it is. And infrared, we talk about 640 by 512s and big imagers are a megapixel, huge imagers are 4 megapixels, right, in the infrared. And so we're dealing with much smaller resolution. Yes, but it matters on what you're trying to detect. These are this, as I said earlier, it's your ground sample distance. It's how many pixels on target do you need to detect something. Do you need that fine a resolution? Like we need that fine a resolution on our cameras because sometimes you blow up the picture or you're zooming in on things and you're breaking into multiple colors, right, to be able to get the full vibrancy of the image. But in the infrared range, we're not looking to do those things, right? Like we're looking to do a detection, and do we need that detection down to, the millimeter, or can we do it at a foot range, or or a meter or 10 meters? This is kind of the question, and do you need that kind of resolution to achieve the mission you're trying to achieve? And I'd say most of the time, a 640 by 512 takes care of the job, right? Sometimes you need a megapixel if you need a larger area. And as Francois alluded to, sometimes a line scan camera works really well because it's fast. Because you're going down a factory line where it's a conveyor belt that's moving at incredible speeds, right? And you've got a big imager. It takes a long time to download all those pixels, right? But if you have a line scan camera, you can do it very, very fast and do your differentiation fast. So, um, you know, do you need all those pixels? And a lot of times the answer is I'm going to say no to do the detection you need. Uh, 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 Brian, maybe you see something different, or Francois.
I would say absolutely. I mean, if you're examining pills on a conveyor belt at a million pills a second, yeah, you don't necessarily need, huge resolutions to determine whether or not you have something contaminating. I can envision, and I don't know that I could say anything more than that, but I can envision defense applications where you probably need resolutions as high as you can possibly get, for reasons that I won't go into, but are pretty obvious. But again, it all depends on the question you're asking. If you're looking for the presence of something or the absence of something, you don't necessarily need a huge resolution.
And I would add to that that sometimes when you're looking and you're adding filters, that means that sometimes you're filtering out a lot of the incoming light. And so using a filter, you're sometimes in, in photon starvation mode. So you need to have a longer exposure time. So actually having a bigger pixel is sometimes more convenient when you're doing spectral response because you need you don't want to have a very long exposure time to compensate. So sometimes it's interesting to have a bigger pixel and not necessarily the resolution. So it's not necessarily the resolution that gives the performance,
Right.
especially when you're doing filtering out information and data.
Right. So for kind of mostly for industrial applications, we're not trying to sort of blow up an infrared image to make a nice piece of artwork or something. So it's fine to not have that much resolution. Um,
I wouldn't necessarily say that it's linked to the industrial market. Sometimes in the industrial market, you need the resolution. For example, in wafer inspection, you need the resolution because you need to see all the details in the wafer, and you need to do a high speed rate inspection. So the more the pixels, the faster you can do the inspection. So it's not necessarily linked to what you're doing with it. It really depends. But when you're using filters, you're really using the spectrum information, which is more of importance. So that's where resolution is less critical. It's more the application with spectral filters that it's of interest to having the higher sensitivity and not necessarily resolution.
That's a good point. So moving sort of around the band, let's say, if you could tell me more about shortwave infrared imaging in particular. So are there any sort of customer success stories that you can share? Maybe Francois, if we can start off with you around shortwave.
Well, as a success story, of course, there's a lot of drones running out on the field with filters in order to do crop inspection to detect to do intelligent watering systems. So you don't want to waste your water. So you need to know what are the areas that are in a drought, and those that are correctly watered. So that's of course a first I'd say application where there's a higher volumes and of course um, and used almost actually almost every day. Then we have more R&D technologies where we've implemented, for example, FabriPero MEMS solutions cavities, so you can really tune and adapt your filter at the moment. So you can really choose your window filtering when you want, and we put that on a drone. So that was a something that was of high interest because on a very small DJI drone, we were able to fit a FabriPro cavity, MEMS cavity in front of a SWIR sensor. So that was of course of interest for scientific applications.
And Martin, are there any sort of successful application projects you can share with us?
I've had tons. In the SWIR band, always the big thing was always water detection. Francois alluded to it with crop health, done numerous types of that, but industrial applications with paper drying, the amount of energy you use to dry paper, you want to minimize that. just get the paper dry enough. And so looking at the water content in the paper is huge. And we've talked about inspection applications. There's been a myriad of inspection applications where you're looking at foreign object detection on a factory line to make sure that something doesn't drop into your packaging methodology, from the line, and you want to differentiate these things. Um, Fruit inspection as well, just to make sure you have the properly fruits picked at the right time, and is sorted. You're sorting stems from the actual fruit as well in your de-stem applications, because you're looking at water content of one versus the other. Um, I hate to say it, in the SWIR band, I'd probably say uh, I'm going to say about 70% of the stuff I look at is usually having to do with water content or something to do with water in the SWIR band. Once you get into what they call extended SWIR, beyond what InGas picks up at 1700, you start to look at mineral contents, and you can start to pick up various minerals, and you can do differentiation between like copper and magnesium and various other things by looking at the reflective properties, and in mining and industrial applications. So Francois hit my favorite, which is crop health. But after that, there's all these industrial things looking at water, and that's in SWIR. That's always been the biggest thing.
We might be accused of colluding before we gave the talk here, but the first thing I had on my list was crop measurement as well. Water retention, drought conditions, water quality issues are huge, and the applications are going at the moment, everything from, as we've said a number of times, suborbital, all the way down to actual feet on the ground, measurements from wells to determine water quality and purity or not, that sort of thing. That's huge. Semiconductor imaging and overlay metrology has been huge for us. Even because of its non-destructive imaging of various shapes and scribe, when determine their scribe errors or circuit misalignments on the chip and that sort of thing. The one that I like, and it's because I'm a biologist by training and I get to hear all of these things, secondhand. But art restoration and investigations are kind of cool. The ability to go underneath the paint to look at the canvas and see what exists there. That's pretty neat. Looking at a Da Vinci and looking at his pencil work, whether or not that's strictly SWIR work or closer to NIR, I don't remember. But I always thought that was pretty neat as a success story to be able to investigate, the origins of world famous artworks. The other example that I had is one that I don't think anyone's mentioned at this point, but which is hyperspectral imaging. Coming again from biology, doing multiple bands simultaneously or multiple regions of wavelength interest is old hat, who've been doing it for dozens of years. In the SWIR, it's sort of burgeoning in that with these hyperspectral imaging paradigms, you have the ability to measure a broad range of wavelengths across distances, time, across spectrum, to be able to derive sort of a two-dimensional or even three-dimensional or even four-dimensional map of what materials might be present sort of in real time as you investigate the substrate. And Martin mentioned in things like geologic inspections, you have the ability to fly over a rock formation and determine exactly where individual types of minerals are present in real time, or close to real time. Obviously, there's a little bit of an image analysis there, but it's the ability to look over a very broad range of wavelengths and pick out exactly what's there based on its spectral properties. I find that extraordinarily interesting, and of course, the applications there are practically limitless. I mean, environmental monitoring is a huge one, obviously. Again, food safety and drug quality control. Again, back to the art analysis or restoration things, and certainly, again, it's a no-brainer for security, intelligence, defense, to be able to fly over a particular geopolitical area and determine in real time what's present, and where it is, and do that over multiple wavelengths for multiple sort of things of interest. that kind of goes without saying is a burgeoning industry.
Yeah, yeah. And while we're talking about moving along the wavelength range and specific applications, there's another question that came in, which are what are the key challenges using long wave infrared thermal bands in cell phone cameras? Are we moving in that direction or?
Well,
I'm sorry.
sorry, go ahead, Brian.
No, I would just say that at this point, chroma in particular, really, we're not moving that far out into the spectrum. Certainly, the urge and the impetus is to go that far out. But right this moment, we're more focused on up to about 3 microns, just from a pure production standpoint. But the work is apace to move further and further out into the spectrum.
Yeah, actually, the long wave, there's already a lot of add-on modules that exist for smartphones. But today, the main applications is essentially for workers in the electrical field, just trying to check out where there can be electrical wiring inside a building. So it's more a professional application than any industrial applications. But for that is for smartphones. I mean, of course, for long wave for other applications, there's multiple requirements. But if it goes along the smartphone, usually it's for professional electricians or professional teams that want to inspect the heating insulation of a building. Kind of application.
What about you, Martin? Can you see this happening at some point in the future, going into the long wave in cell phones?
I, they're right. There are attachments now. Actually, I own one. It's a great little device to find heat leaks in your house, or as Francois said, to look at electrical from a filtering point of view. The only thing I've really seen on filtering in the long wave infrared in industrial is when people are actually trying to do precision temperature measurements, and they'll use what we call two color. It's two wavelength, and you use multiple wavelengths in the long wave or mid wave infrared to actually really differentiate temperature to get more precision temperature measurements on an object. You know, if you're monitoring a motor system and you want to see whether it needs maintenance, right? Instead of setting up a maintenance schedule every 6 months because you know the motor wears out and you're taking your chances, you could actually look at it thermally and look for hot spots and determine, oh, now this needs maintenance, and whether that's on a cell phone, that may be a little much, but that's where we're seeing these thermal cameras for monitoring industrial applications on cell phones. Yeah, they're there, and as Francois said, I think it's for professional. I don't know how much, whether they'll be fully installed into the cameras and used for that kind of thing. I'm not sure I see that in the near future. There'll be other applications for long wave around, but I'm not sure on the cell phone, other than as attachments.
Okay. And so, I mean, just we're running short on time, but if I could just close things out with one last audience question here, which is talking about the broad wavelengths. So let's say you've got a detector that works in a broad wavelength range. The example given is 900 to 1700 nanometers. Is there a chance that the image contrast differs when the illumination wavelength is changed within that range?
Oh yeah, it will definitely change. Your contrast as a scene will change based on the illumination levels and the reflectivity or the absorption of the object you're looking at. If you're changing that illumination level, the contrast will definitely change, and how the material interacts with the light is important. It's very similar to what happens in the visible, right? Where you turn off the lights and your contrast of the scene changes. It's not very much different in shortwave infrared. I'll admit in midwave and long wave, you see less of that because now it's thermal output, right? And so the amount of light that you're projecting out there isn't changing it as much because it's more an emissive band. But in the shortwave infrared, we're more closer to our visible cousins, as I say, and you're looking at reflective and absorption in the image in the object, and so you change that illumination level, your contrast is going to definitively change.
I would add, and it's not, again, it's relying on my own background basically, but when you're dealing with infrared light, yeah, the illumination intensity is going to affect the contrast, but it's not going, that intensity change isn't going to actually be damaging to your sample in most cases, I would imagine. Going back to the biological world, you shine a bright enough light of any wavelength on a biological sample, and you're going to do damage to the sample itself. That's not beyond fluorescence, beyond any other photochemical process. You shine a bright light. I mean, it's the reason we're not all staring at the sun. Same difference. The intensity can be bright enough to damage the sample. In the infrared, if my understanding is correct, and it may not be, the sample itself isn't being necessarily changed by the illumination itself. So you don't at least have to deal with that variable in your imaging. And maybe I'm wrong. Maybe I'm barking up the wrong tree, but that seemed to be one point to make.
Well, sometimes in the midwave, you actually want to filter out the lower wave bands to be able to avoid the incoming light and only have the emissive part and don't want any reflective part. So sometimes you're doing it the other way around. You just don't want that reflective light.
So that's a good way to sort of minimize the effect if it is something that you don't want. So I mean, well, I think we've run a little bit over time, but that's just about all we've got time for then. So for today's discussion, but if you did miss anything, you'll be able to watch the session back on demand via the Electro Optics website for the next 12 months. There's a lot more to discuss regarding thermal imaging and optical filters, of course, just by the fact we've run over time today. We've only just scratched the surface, but you can stay up to date on the subject at electrooptics.com. Also on the website, our next live panel discussion will put the distributors themselves in the hot seat. It's titled UK Photonics Distribution, what manufacturers, startups and OEMs need to know. The online panel will include marketing executives of some of the UK's most prominent photonics distributors. They'll give their frank perspectives on the current state of the market, the challenges they face, and what they need from their partners. So make sure you don't miss out on that one and sign up for that now. But for now, there's just time to say a big thank you to our guests for joining us and sharing their insights with us today. Please invite them to follow them on LinkedIn and their companies and stay up to date with them and their companies. And a big thank you also to you, the audience, for watching. So thank you and goodbye.
Thank you, gentlemen.
Good day. Thank you.